Let me ask you something before understanding Poisson distribution. How many emails do you usually get in an hour? Or how often do you see typos in a printed book? Or what's the number of road accidents at a traffic signal each day? These events don't follow fixed rules. They just happen randomly, unexpectedly, and sometimes all at once. There is no definite number of trials, no clear success or failure. All we care about is how often something happens. This is exactly where the Poisson distribution come in. In this video, we are going to understand when and how to use the Poisson distribution, its formula, moments, skewness, kurtosis, and how it behaves graphically. Hi everyone, I am Bindeshwar, and without further delay, let's get started. So in binomial distribution, basically we deal with events whose occurrences and non-occurrences are almost equally important. However, in some situations, or real life situations, events do not occur as outcomes of fixed number of trials, or events occur randomly over time. Interest lies only in the number of occurrences. For example, number of printing mistakes per page in a book. Second example, number of defects in production per item or number of accidents during a time interval. So such cases are not suited for a binomial distribution because number of trials n is not definite, probability of success p is very small. In such cases, Poisson distribution is used, and that was introduced by S.D. Poisson in 1837. And basically, Poisson is a limiting case of binomial distribution under two conditions. N tends to infinity, that means n is very large, and p tends to 0, that means p is very small. And np is equal to lambda, a finite constant. Now let us define Poisson distribution. So a random variable x is said to follow Poisson distribution if it assumes an indefinite number of non-negative integers and the probability mass function. It has probability mass function because it is a discrete distribution. E minus lambda, e raised minus lambda, and lambda raised x upon factorial x, where x is 0, 1, 2, 3 and so on, and lambda is greater than 0. Now where lambda is mean number of occurrences in a fixed interval and E, that is equal to 2.7183. Now let us calculate moments of Poisson distribution. So rth order moment about origin of Poisson variate x is expected value of x raised r, and you can express like this. So here if you put r is equal to 1, so you will get the following expression, and you can calculate like this one. Take e raised minus lambda outside, so you will have this expression. Thereafter you can write lambda raised x like this one, so x will get cancelled, so in denominator you will have x minus 1, and thereafter here again you can take lambda out from the expression, and you can recognize that is nothing but e raised lambda. and finally you will get this one, and thereafter lambda, that will get cancelled. That means power would be 0, and thereafter mean is lambda. That means first moment is mean. Start with the definition for the second moment. So mu prime 2, that would be x square, and the distribution. Thereafter we will use this identity. This is very important, and thereafter everything is like you have calculated the first one. So you will write like this one, x square, and thereafter probability mass function, and thereafter just distribute this one over two expressions. So we will have this one, and thereafter here you can recognize that that is nothing but lambda, and here let us solve this one. So we are going to solve here. E raised minus lambda you will take out, and thereafter you will have this expression. Thereafter you will have e raised minus lambda here, and here this one is lambda here, and here is also it will come with minus e lambda already, and thereafter here this is e lambda, and here this is also e lambda. So that will means power will get added, so power will be 0. So finally we will have this one, like this one. Just I want to tell, e minus lambda you have already here, that is lambda square e raised lambda plus lambda e raised lambda. So already we have, so e minus lambda plus lambda square plus lambda, that power is added, so that would be 1. Finally we will have this one. Now so second raw moment is lambda square plus lambda, and variance is defined as mu2 prime minus mu1 dash square, and if you put, so we will get variance as lambda. So mean and variance both are lambda. Now third raw moment is e expected value of random variable x q. So here because q, so here it would be q, and here the probability mass function. Thereafter again here the trick, instead of xq we are going to use this expression. So there would be three expressions we will solve, and we will get. So let us see same pattern here. So mu prime dash here, so expressions are written as a, b and c, and just a is given, the first one, second b, third c. So if you solve, so first a you will get aq, b 3 lambda square, and c lambda, and finally mu prime 3 would be lambda q plus 3 lambda square plus lambda, and the third order central moment would be lambda. If you, because central moment can be expressed in terms of raw moment, so that would be lambda. Now fourth moment, fourth raw moment, that is, So expected value of random variable x raised 4. So the same here. That is the again that is the important. We will use that identity. So we will have this 1, 2, 3 and 4 expressions, and we will solve them separately. So here A, that is B, C and D, and if you solve, so A is lambda raised 4, B 6 lambda q, C 7 lambda square and D lambda. And here this means mu prime 4, that is lambda raised 4 plus 6 lambda raised 3 plus 7 lambda raised 2 plus lambda. And central moment can be written as in the form of a raw moment like this one. So that would be 3 lambda square plus lambda. So skewness, that would be, that is standardized third moment. So if you plug all the values, so we will get skewness 1 upon lambda under root. And kurtosis, that is the fourth moment, standardized 4 moment. So mu 4 we have already calculated here, and the standard deviation is square, so that is lambda square. So we will get 3 plus 1 upon lambda. So here Poisson distribution is positively skewed because skewness is positive. It is leptocotic when lambda is small. Now you can see the plot when lambda is equal to 3, and you can also see the plot when lambda is equal to 10. So when the value of lambda is increasing, the shape of distribution is becoming symmetric. So when lambda tends to very large number, so the distribution will become symmetric. So hope you have understood the concept of Poisson distribution. For more resources, you can visit www.postnetwork.co, YouTube channel PostNetwork Academy, handle is @PostNetwork Academy, Facebook page PostNetwork Academy, LinkedIn page PostNetwork Academy, and also GitHub repositories PostNetwork Academy. So hope you understood. Thanks for watching the video.